Hi folks, welcome back to the next lesson in P4, which is, I don't know, about lesson 6 or something now. This one's about irradiation. It should say irradiation and contamination at the top there. I've missed that out. So irradiation and contamination is what this one's about, and I want to basically just describe what irradiation is, and contamination I suppose. There's 3 questions there, we'll get to those in a second. So outcomes wise, things I want you to be able to do by the end of this are explain what is meant by irradiation, describe the difference between contamination and irradiation, and then explain the importance of communication between scientists. So that's like a little bit that's tacked on at the end, but it is important to know anyway. There's some key words: irradiation, contamination, mutation and repair. We've kind of used these two a little bit I think in a previous lesson, but we're going to do it in more detail today. And there's 3 questions on here that I want you to have a go at. Just spend, I don't know, a minute or 2 on each one, max. So pause the video, give those a go, and yeah, see how you do. The last one might have you having to do some research to figure it out, or unless you've got a good memory, it's something we did in school. So pause the video and give that a go. Okay, let's go through those. So the first one, write the nuclear equation for this undergoing alpha decay. So you've got uranium 235 and 92 are the numbers. So 235 is the mass and 92 is the atomic number, the number of protons. So it says it's undergone alpha decay. So if you used to write this down, first of all you'd write U 235 plus 92, and then you'd show an arrow saying that something's been emitted, as in it's given out. And what you draw next is helium, He, capital H, lowercase e, and that's got a mass of 4 and it's got an atomic number of 2 because it's given out an alpha particle which contains 2 protons and 2 neutrons. And as we discussed previously, if something contains 2 protons, it's helium. So it's a helium nucleus that's been emitted from the nucleus of uranium. Now that means that you've no longer got uranium. You started off with uranium and 2 protons and 2 neutrons have been ejected, so you end up with a different substance. So the mass there would have dropped down to 231 and the atomic number would have dropped down to 90. So let me just get my periodic table app out because I forgot to get that started. So once you know that you've got an atomic number of 90, you just go to the periodic table, find something that's got an atomic number of 90, which in this case is thorium. Okay, so that is what your nuclear equation would look like for an atom of uranium-235 undergoing alpha decay. Okay, so uranium, and then an arrow to show that there's emission, and helium plus thorium with the right numbers on there, obviously. Yeah, so that's the first one. What is ionizing radiation? That's just radiation that can cause something to become an ion, to cause an atom to become an ion, so either gain or lose charge. What is the specific heat capacity equation with units? I have to think myself here. So it's the change in energy is equal to mass, change in energy is measured in joules, that's the unit, is equal to mass, which is measured in kilograms, multiplied by the specific heat capacity, which is measured in joules per kilogram degree C, and then multiplied by the temperature change, which is measured in degree C. So that is the specific heat capacity. Without the units, because I've just given you, it is change in energy is equal to mass multiplied by specific heat capacity multiplied by temperature change. Right, let's jump straight into it then. So radiation suits, you've probably seen something like this on TV or in films or whatever. They're used by people that deal with radioactive materials. But why is this done? Why are they wearing these things? Just have a quick think about it, see if you can tell me. If you think it's to protect them from radiation, you are unfortunately incorrect. It is not to protect them from radiation, it's to protect them from contamination. Okay, so the suit itself doesn't offer any protection against radiation. We've talked about gamma being able to pass through concrete and lead. That rubberized suit isn't going to stop gamma. A beta source, if it was actually on that person, would still be able to get through it as well. Alpha would probably be blocked by it, but it's not there to block radiation. As it says there, think about the penetrative power of the types of radiation. The suits are used to deal with the threat of contamination. Okay, so we're going to talk about what contamination is in a second, but that is one of your principal concerns if you're dealing with an area that is radioactive or has had a nuclear incident. Contamination is a big problem. Okay, because it can have if you're exposed to radiation, that's bad, but if you're contaminated, you are consistently exposed to radiation. Right, irradiation then. Simply put, irradiation is a process of exposing something to radiation. Okay, so let's have a think about that then. We've got 3 different punnets of strawberries there. A punnet's just a name for a collection of strawberries. So I want to know which one you would rather eat and why. So have a think about it. The first one, it says, these have been irradiated with gamma rays. This one says, these were contaminated with radioactive rain after a nuclear disaster. And then this last one says, these were picked and put straight in the box. So which of these 3 would you rather eat and why? Now, it would make sense to jump straight for this one. These were picked and put straight into the box, but there's things living on things that live outside, if you get what I mean. So you're going to have things like bacteria, microorganisms, insects, all sorts of things that could be living on those strawberries, and if you're just happily eating them and haven't taken that into account, that could make you ill. These were contaminated with radioactive rain after a nuclear disaster. I wouldn't fancy eating that. That's going to be as bad as it sounds. These have been irradiated with gamma rays. Yeah, I'll eat those, no problem. And chances are you've eaten things that have been irradiated with gamma rays as well, okay? So in this case, irradiation has been intentionally used to destroy the bacteria on food, making it safer to eat. So by exposing these to gamma rays, we've managed to kill off the bacteria, we've managed to kill off any microorganisms, we've managed to kill off any insects that are on it. The radiation has actually damaged the cells of the DNA of the bacteria, microorganisms, whatever it is, and killed it. So they are no longer going to pose a threat to you if you were to eat the strawberry and they were on it, because, well, they're dead. What's this got to do with radiation suits seen in the previous picture then? Well, we need to talk about contamination for that. So contamination is the unintentional transfer of a radioactive source, as in something that is giving out radiation, onto an object. So it does cause some confusion, this, but if you stick with it, and you might need to rewind and go over this a couple of times to really get it, you should get it in the end. So an example of irradiation then. Gamma or X-rays can be used to destroy germs or bacteria on food or medical equipment, and it is frequently used for both of those two purposes, and it makes them sterile. Sterile as in there's no bacteria on them, or if there are bacteria on them, they're dead, so it's not going to cause any problems. So it's completely clean. When finished, no radioactive material remains on the object. It's not radioactive. So if you're a surgeon, for example, and you're using scalpels and medical equipment that has been irradiated using gamma rays, the actual object itself, after it's been irradiated thanks to gamma rays, poses no threat to you at all. It's not giving out radiation, it's not radioactive. It's been subjected to radiation, but it's not itself radioactive. Contamination is different, okay? So contamination, a source of ionizing radiation is transferred onto an object. So remember, a source of ionizing radiation is something that gives out radiation. So let's say, for example, this is a lump of uranium. That is a source of ionizing radiation, because that uranium that this is made out of is ejecting ionizing radiation. Okay, so now if this was to end up on something, as in attached to it, let's say you're walking around Chernobyl and a bit of dust that's radioactive lands on you, you're now contaminated. You have something on you that is radioactive, is giving out radiation, so you are now contaminated. So the object is now emitting radiation, and I've put in brackets there, technically the source is the thing that's giving out radiation, that's emitting it, but the thing itself now poses a threat because it's carrying that material around. So that is the difference between irradiation and contamination. I'll be honest, teaching this in lessons in school at this point is still not clear. Students still don't get this. So I've got another example for you, so let's see if this one makes it a little bit better. So think of it like this. When you turn a light on, that room gets filled with radiation, electromagnetic radiation, in the form of light. So if I turn my light on now, the light comes on, the room is filled with light. If I turn that light off, the light goes off instantly, the radiation is gone. Nothing in this room is giving out light, all right? Ignore things. The explanation in a minute is going to make you think, oh, it's glowing in the dark. Don't think of it like that. I just mean the light that was coming from there is now no longer in the room. The room is now pitch black. This one at the bottom, this explanation at the bottom, imagine you turned a light on and off again, and some of the objects that were previously non-luminous, so let's imagine like my desk, I turn the light on and turn it off again, and all of a sudden there's little dots of light all over the table, like there's light coming off the desk. In that case, because that's now emitting that, we'd say that that is contaminated. It's as if some of the radiation was passed onto them, was transferred onto the actual substance, the surface itself, okay? So in this example, this is irradiation. Something's been subjected to radiation, but it's not after the fact giving radiation out. And this is contamination, as in something's been subjected to radiation. A radioactive source has ended up on that thing, and that thing itself is now giving out radiation. So that's the difference. So you could kind of understand why suits are useful in that scenario. You could put a suit on, walk into Chernobyl, you're still being irradiated, you're still being subjected to radiation, but then after the fact you come out and you get totally hosed down, cleaned down, and then you take the suit off and you walk away and you haven't got anything on you that is radioactive, so you are not contaminated. The suit is, and I don't really know what they do with those suits after. I don't think it'd be safe to clean them. I imagine they're probably disposable. They probably bin them after it. But it stops you becoming contaminated, because you could then pose a threat. That doesn't just pose a threat to yourself. You could then pose a threat to other people. Imagine you work in that industry and you've gone into Chernobyl to do some cleanup or any kind of nuclear environment, and you do something, you get contaminated and you don't realise, and you go home, and then you are irradiating your family. So it's obviously important that we try and avoid contamination where we can. I mentioned irradiation before, and the fact I have mentioned radiation before in a previous lesson, and the fact that you're subjected to it. But let's just look at some numbers, because this is quite interesting. So this is just a typical person here. In terms of how much irradiation we get as a human, from the sky, about 400,000 cosmic rays pass through us each hour. 400,000, so nearly 500,000 cosmic rays every hour pass through you as a person. This is an average, obviously. From the air, 30,000 atoms of radioactive gases get breathed in and disintegrate in our lungs each hour. This is sounding horrendous so far, isn't it? From food, 15 million potassium-40 atoms disintegrate inside our bodies each hour. So bear in mind, each of these is ionising radiation. And then down here, from soil and building materials, more than 200 million gamma rays pass through us each hour. So this is a ridiculous amount of radiation that you're being subjected to every single hour. Is that something to worry about? Not really, okay? So not only is there nothing you could do about it, humans are pretty good at coping with the being subjected to this amount of radiation at all times. Our body can kind of handle it. It's used to it. Okay, so all these things will be doing damage to the body, small amounts, mutating DNA here or there, damaging cells, but then the body either deals with it, they'll fix it, or they'll get rid of those cells. Either way, your body can cope with it. The problems start when you get subjected to more radiation than normal, okay, and your body can't keep up with the repairs and getting rid of the dodgy cells. That's when you start to end up with problems such as cancer, basically. So let's look at those then. Let's look at the chain of events that could lead to essentially cancer, okay? So we've got the DNA of a cell in a human body here, just whatever cell you want, it doesn't make a difference. What could happen is radiation could get to the DNA of that cell and it could damage the DNA of that cell, the instructions that tell that cell what to do, okay? One of the possible outcomes of that is you end up with a cell with a damaged nucleus. Now you don't really want cells with damaged nucleus because it's not going to do the job that it's meant to do. It might end up turning into something else. So damaged cells either die, which we'd call cell death, or attempt to repair the damage, okay, so you'd end up with a repair. So that might end up with cell death, as in the cell gets damaged beyond repair, so it dies, and then another cell will pop up and take its place. It could happen that it gets fixed, and then you end up with an accurate repair, and you end up with a normal cell. So that cell was damaged, it gets fixed, and now that cell's going to crack on doing what it was doing beforehand. What could happen though is in this repair process, if it gets misrepaired, as in the actual DNA ends up being fixed, but it gets fixed and it's still technically not right, you could end up with a cancerous cell, okay? And if the cell's not repaired properly, it says it may develop into cancer. That's a problem because you get one cell that's misrepaired and it's the wrong type of cell in the wrong area. So let's imagine you've got like a lung cell growing in your brain. That cell then starts to divide and divide and divide, and you end up with lots of those. And you don't want any other cell in your brain apart from brain cells, really. So that is why cancer is such a problem. One of the outcomes at the start of the lesson was describe why it's important that scientists share information between themselves. So I just wanted to tell you a little bit of a story here, basically, and hopefully they'll get the gist of why it's important that scientists communicate with each other, share their findings, and basically collaborate. Okay, so this is Marie Curie. You've probably heard of Marie Curie before. She's famous for having discovered radium and polonium, which are two radioactive substances. This is back in the day before we really knew what radiation was, by the way. So it wasn't just like she was being reckless with radioactive substances. The dangers of them hadn't really been discovered yet. She was kind of one of the forerunners that was doing work on radioactive substances, and that's basically what led to her death. So Marie Curie died on July the 4th, 1934 of aplastic anemia, believed to be caused by prolonged exposure to radiation. She was known to carry test tubes of radium around in the pocket of a lab coat, and many years working with the radioactive materials took a toll on her health. So walking around with this thing that she was doing research on, doing work on, she discovered it, and she kept some in test tubes and kept them on her at all times. Basically, she was unknowingly constantly subjecting herself to dangerous ionising radiation. Now this is an example of why it's important that scientists share their findings with others. You can imagine that after this was discovered and the real dangers of ionising radiation were realised, if that information wasn't shared, what was to stop this happening again to other people? What was to stop people making loads and loads of radium, thinking, oh, this is useful and I could sell it or do whatever I want with it, and then they die, people around them die, they irradiate, all sorts of things. So it's really important that scientists share their findings with others, not just regards radiation, but everything in science. Okay, all scientists around the world are working together to improve the understanding of humanity as a whole, not just individuals. And we can kind of stand on the shoulders of those giants and keep progressing as long as information gets shared between scientists. So let's just have a quick look at this. And so this is based on the stuff that I've just been talking about, but it's worth stopping a kind of learning checkpoint and just recapping what was said and are you happy with it, familiar with it, understand what's going on. So this little box at the top has got some keywords and some definitions, and you'll notice there's some missing. So in this case we've got the keyword but no definition. In this instance we've got the definition but we've got no keyword. So I just want you to fill in those boxes How you do that is up to you. Spare piece of paper, do it on your phone, I don't care, it's up to you. Print it off if you like. You'd have to print screen it and print it off though, obviously. So fill in those blanks, and at the bottom, this is identical to the diagram I showed you a second ago, and there's just some blanks about it. So if this happens, what is this called? What's this cell called? What's this cell called? What's this cell called? So just try those, pause it, spend a couple of minutes on that, don't spend ages. I'm going to go through the answers in a second, so just pause the video and try that now. Okay, let's go through the answers for that. So irradiation then, the definition of that is exposing an object to nuclear radiation, just exposing it to it. This one, the use of gamma rays to kill bacteria, is sterilisation. And you've probably heard of sterilisation before, as in something has been sterilised. And if it's sterilised, then it doesn't pose a threat to you in terms of like bacteria or microorganisms. Mutation is when there's a change of DNA. So DNA is meant to be however it's meant to be in a normal cell, but then obviously radiation could cause a change in that DNA, and we call that mutation. Contamination is the unwanted presence of materials containing radioactive atoms. So you end up with a radioactive source in a place where you don't want it. Well, that's a contamination. Yeah. Misrepair, the definition is a cell in the body is repaired incorrectly. And then finally, if a cell is repaired correctly in the body, which is just an accurate repair, or a repair, I suppose you would call that. So those are the keywords and definitions there that we've been using throughout the lesson, and we will continue to use in other lessons as well, so worth remembering. This diagram, I'm not going to read through it all because I've just read through it all on the previous slide, but I am just going to show you the answer straight away. So if the cell is damaged beyond repair, it'll die. If it's not damaged beyond repair, a repair will be attempted, and if it's an accurate repair, you just end up with a normal cell. But if a repair is attempted and there's a misrepair, then you could end up with a cancer cell. Okay, so that is the effect of irradiation on body cells. That's what we've discussed so far. Okay, so hopefully that's been useful to you. Let's just move on a little bit. There's an exam question here that I'm going to have a go at, and it doesn't just draw on stuff we've talked about in this video lesson, it also draws on stuff that we've talked about in previous lessons. So pause this, take as long as you want. I will stress that usually though, exam questions, we say a minute a mark. Okay, so there's 5 marks there, so realistically you shouldn't be spending more than 5 minutes on this. In a real exam though, remember that you can kind of adjust that, it's dynamic. So for example, the 2 last questions are 1 mark each. If you can spend 30 seconds each on those, you've just got yourself another minute for the slightly longer question. So pause the video, rewind it if you want to. I don't care if you do a bit of research either, to be honest with you, to help you out, but try those questions and then I'll get back to you in a second. Okay, let's go through those then. So this one says, food irradiation is a process that exposes food to radiation. Irradiation can be used to kill the bacteria that cause food poisoning or to slow down the ripening of fresh fruit and vegetables. Frozen foods and food inside packaging can also be irradiated, and the table gives information about 5 radioactive isotopes. Which of these radioactive isotopes would be most suitable for irradiating food? So let's have a quick look at the answer there then, if it pops up. So cobalt-60 is what you should have gone for there, okay? Now if you've not got cobalt-60 in there, that doesn't mean you've got 0 marks here. You can still get some marks even if you've got the first part of this answer wrong, okay? If your decision for the explanation is right, even though your answer is wrong, you can still pick up some marks. So that should say cobalt-60 at the top. Explain the reasons for your, that's worth 1 mark by the way. Explain the reasons for your choice. Well, the gamma radiation will pass through food packaging. If you look at it, cobalt-60 gives out gamma. Okay, now you might have said, oh, we're going to use technetium-99 because it's got gamma. So if you've mentioned gamma there, you can still get a mark, even though technetium-99 is the wrong answer for the which isotope to use. So the second bit, the gamma radiation will be able to pass through the food and the packaging. Okay. The last one, you should have said it's got a long half-life. So the level of radiation is, it says fairly constant for a number of years. Okay, so you might have picked a different one and gone, oh yeah, I'm going to go for strontium-90 because it's got a really long half-life, so it'll last for ages. Great, your strontium-90 was the wrong choice, but your reason for choosing it was actually correct, so you can still pick up a mark there. So these are the 3 marks there that I want you to have a look at. It doesn't have to be word for word, by the way, as long as you've got something that is equivalent to what's been said there, you can still get the marks. Okay, so cobalt-60, because the gamma radiation that it emits will be able to pass through packaging and everything else, and it's got a long half-life, so it's going to be a fairly constant amount of radioactivity on it, and it's going to last for quite a while. Okay, the next bit, it says, many people think that food should not be irradiated. Consumer groups have said that they are worried about the nutritional value and safety of eating irradiated foods. Suggests one reason why some people may be concerned about the safety of eating irradiated food. So this isn't saying it is dangerous, by the way. Don't fall into that category of poorly informed people that decide to form an opinion before actually understanding the situation at hand. Inform yourself. I've discussed it today. I've said you've eaten food that's been irradiated already. Has it done any harm to you so far? Well, no, because it's not going to do any harm to you. But let's suggest one reason why people might think that it's a safety concern, okay? So people might link the use of radiation with illness and cancer. So people hear the word radiation and think, oh, dangerous, 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 I don't want anything to do with it. Well, realistically, in this situation, it's not dangerous at all. In fact, it's safer for you for your food to be irradiated, but they may still think that, okay? You might have said they think that the food becomes radioactive. Again, absolute nonsense. It doesn't become radioactive, but people might think that, okay? There's no cure for idiocy, I'm afraid, so some people might think, because they've got no idea and they've done no research, that if you subject a food to radiation, that is now radioactive and it's going to turn them into the Hulk or something stupid. Another acceptable answer, they might think it's harmful to them, and it refers to irradiated food in that situation. So they might think that if you irradiate food, that makes it more dangerous for you. Again, not reality, but some people might think that. Okay, finally, so question 1b, part 2. Independent scientific committees in several countries, including Sweden, Canada and the UK, have concluded that it is safe to eat irradiated food. Well, no surprise there, because it is safe. These scientific committees need to be independent from government influence. Suggest why? Well, the answer is here, basically, in a nutshell. So it's not biased and it can't be influenced by government views. You can imagine that irradiating food is probably not a cheap process, and people that are producing this food, in order to make lots of money, want to keep their costs down as low as possible. You could also imagine that if they weren't independent, these scientific committees, if people could have some kind of influence over them, they might be able to persuade them to say, oh, do you know what, you should go out and you should say that irradiation actually makes food dangerous, and then we won't have to do it, and then it'll save us a fortune. Unfortunately, that does happen in places in the world, but usually the scientific community is kind of immune to that stuff. Part of the scientific fraternity, if you like, is the idea that we should always try and strive for results without bias, regardless whether that answer is the one that we want. So those are the answers there to your exam question. I think that's it. Yeah. In your books, you've not got your books, so you can't do that bit. Okay, so that's all I'm going to go through today. Hopefully that was a quick one. If you've got any questions, ask them in the usual way. Ask your normal teacher or ask me, I don't mind. And if there's something you don't get, rewind the video, go back over it. Do a bit of your own research. YouTube is a good research tool. You could go on there and just watch a quick 5-minute video on something like the difference between irradiation and contamination. That might help you out. You're probably watching this on YouTube as it is. Okay, I'm going to call it there. See ya.